In this video, we're going to discuss our last category of functions, which we call logarithmic functions. So logarithmic functions are very closely related to exponential functions, which we discussed in the last video, but seeing them the first time, they usually are a little bit mysterious. So we're going to kind of layer in a definition for what a logarithm is. So first thing we need to talk about is the idea of an inverse function. So we use inverses all the time. We use them specifically when we solve equations. So operations that are considered to be inverses are going to reduce one another. Sometimes you use the term cancel out. So for example, if we have a multiplication and we want to get rid of it, we use a division. If we have an exponent and we want to get rid of it, we use a radical. So these are called inverse operations in the sense that they are opposites. In this case, the opposite operation will cancel out whatever we're interested in canceling out. So if we were to build together a bunch of different operations to cancel out a bunch of different other operations, then we can create what we call an inverse function. So an inverse function is going to take all of the operations represented in a function and it's going to cancel them all out. So for example, say we had a function where we took our input, we multiplied it by a constant, and then we added another constant. Well, the inverse function for that particular function would have to cancel out both the multiplication and the addition. So an inverse function is just going to take all of the inverse operations that are needed to cancel out a particular sequence of operations in a particular function. Now, why is it called an inverse? You have to think about what the word invert means. What does it mean to invert things? Inverting means switching. So say for instance you have a black and white photo. If you were to invert the colors in the photo, then all of the light colors then become dark, and then all of the dark colors are then going to become light. I want you to also think about what would happen if you were to take the original photo and then take the inverted photo and lay one on top of the other. Well, all of the dark colors from one would fill in all of the light colors from the other and vice versa. So if you were to lay one photo on top of the other, essentially what you would have is a solid black image. In a sense, one of the photos canceled out the other photo. So inverting then gives you something that cancels out. Now, when we're talking about inverting from a mathematical standpoint, what are we actually switching? We're not switching light and dark. What we're switching is x and y, what we think of as our input and our output. So if we take a particular function, identify x, identify y in our function, if we were to flip x and y, then essentially we have inverted that function. If we were to then take all the steps we would need to isolate y again, then we'll have y is equal to what we would call the inverse function of our original. Now this applies if we have an equation or if we have a graph, if we have a set of ordered pairs, anything. If you were to take all the x's, flip it with all the y's, that's going to give us what we call an inverse. Now we're going to need this idea of an inverse to define what we're going to call a logarithmic function. So an inverse function is not really a category, like a polynomial or an exponential function is a category. You can think of inverting or finding an inverse function as something you can do to a function. A logarithmic function is going to be the inverse of an exponential function. So suppose we have an exponential function. We're going to use y instead of f of x, but remember we could have an f of x here. F of x represents the output of the function, so does y. So our function is y is equal to b to the x power, so b is the base for the exponential, x, our input variable, is our exponent, and then our output is represented by y. If we were to take this particular function and then invert based on the rule for inverting, that just means take the x, take the y, and they change places. So if we were to invert this particular exponential function, we would then have x is equal to b to the y power. Now it's important to keep in mind when we invert, x and y still mean the same thing in terms of x being our input and y being our output. So even though y is not isolated, it's now in the middle of an expression, it still represents the output of the exponential function. But now it's moved, it's in a new location. Now what would it take to actually isolate the y? As it turns out, we don't actually have any algebra up to this point that would allow us to take that y and then isolate it again and have y is equal to a new expression. So isolating the y is not something we can really do. Since we can't actually isolate the y, mathematicians just defined a new operation, in a sense, representing this y when we find the y in the exponent of an exponential expression. So when we have an equation like this, our output y is in the exponent, we have a name for this value of y that's in the exponent. We are going to call this y the logarithmic function base b. So the logarithmic function, or the logarithm base b. So these two statements are going to be logically equivalent in terms of what this actually means and how we're going to actually write this term logarithm. So if we have x is equal to b to the y power, which again was the result of taking our exponential function and inverting, this particular expression is going to be equivalent to saying that y, our output, is equal to the logarithm, we're going to abbreviate it as log for log, base b, our b is going to be a subscript next to the log, and then x is going to be our input. So the way we would read this on the right hand side is going to be the log base b of x. Now, just a word of advice, the x right here, even though we don't have parentheses around it, like we would have if we had function notation with f of x, it's understood that x is going to be the input for the logarithmic function. So if we think of this log as telling us to do an operation, to do something algebraically, then we're thinking of x as the thing that we're then doing that to. X is our input. So sometimes you'll see the input without parentheses, sometimes you'll see parentheses around it. I just want you to be aware, if you don't see the parentheses, it's understood that this logarithmic function is applying to whatever is directly to its right. That's what we're going to consider to be the input. So the constant b, in this case, notice b was the base for the exponential function. It's also called the base for the logarithm. So exponential base becomes the logarithmic base, which is going to be the subscript. Now, if we think of this as its own function, every function has a domain, every function has a range. The domain of a logarithmic function is going to be the set of all positive real numbers. So that's going to be numbers that are strictly greater than 0. We can plug in fractional values. We just can't plug in anything that's 0 or less than 0. So the domain is positive real numbers, and then the range is going to be all real numbers. So we can only plug in positive numbers, but the outputs we can get anything all the way from negative infinity to infinity. So we're not going to worry about graphing this particular kind of function, but just for the sake of looking at it and comparing it to what we've already graphed, this is an example of an exponential function. This would be y is equal to b to the x power whenever our base b is a number that is greater than 1. So remember, b is going to be a positive number, and it's going to have to be greater than 1 in order to have a graph that's shaped like this. If this is our exponential function that we then inverted to get a matching logarithmic function, then this is going to be the graph of the logarithmic function. So these two graphs are very closely related. They're related by a reflection. So if you were to take the 45-degree diagonal, the line y equals x, and think of that as your mirror, flipping across that mirror is then going to give you the graph of an inverse function for any original function. This just happens to be the function that we're reflecting. So if we were to take this particular graph, reflect it across the line y equals x, then we get the graph of the logarithmic function. And we can verify the domain and range from this picture. If you think about the x values that this graph covers, it covers everything to the right of the y-axis, in other words, all the positive numbers, all the positive real numbers. And then if you look at the y values where it goes vertically, well, it has an arrow that points diagonally upward. It looks almost horizontal, but it is actually diagonal. So it's going upward forever and ever and ever. And then this arrow pointing down also tells us we're going downward forever and ever and ever. So that means our range is going to be all real numbers. So what does this actually mean in terms of what this logarithm is telling us to do? We know that this is what we're calling the output when the output is inside an exponential, when it's the exponent for an exponential. But if you just see this expression, log base b of x, say you have actual numbers in place of b and in place of x, What does it actually mean? What is it actually telling you to do? You see a number multiplied by another, you know what to do. You see a number inside of a square root, you know what to do. You know what it's asking you for. What is it asking you for if you have something like that with actual numbers? Let's talk about that. Now, before we do that, just a couple little special situations. The most common bases we're going to use are going to be base 10 and then base e. So remember, e was that special number we talked about when we looked at exponentials. E is about, let's see what e is. Remember where you can find e. Here's an e right there above the division symbol, and then e with an exponent is right above ln. So if we were to just use e by itself, second and division, and then hit enter, that's going to give us e. So e is about 2.718. This is a commonly used base for a logarithm. It's a common exponential base, so it's a common logarithmic base. Now, base 10 is also going to be very commonly used because we have a base 10 number system. So our place value system that we use to represent numbers is actually base 10. So we have a ones place, a tens place, a hundreds place, a thousands place. All of those places are considered to be powers of 10. So we have a base 10 number system. Now, because we use these bases so frequently, mathematicians made the decision to abbreviate our logarithmic notation in order to deal with these two bases. Rather than having to write them over and over, we have an abbreviation that takes it and shortens it a little bit. So if we want to write log base 10 of x, rather than having to write the base 10, we just write log of x. So if you see log of x, in other words, you don't have a base written, it's understood that the base is 10. We call this the common logarithm. So the logarithm base 10, which abbreviates as just log and then of x, whatever our input is, that's called the common logarithm. Now again, e is also a common base. If we were to take log base e of x, we actually abbreviate that as ln of x. So rather than log base e, we're going to write ln. ln stands for natural log, and yes, the letters are out of order if you're going to say natural log, but it's going to be l and n, and then it's going to be ln of x. You'll notice if you look on your calculator that you actually have buttons for both of these logarithms. So if you look to the left of the 7 and to the left of the 4, we have a log, we have an ln. That references those particular logarithms specifically. Now, logarithms, one thing that's going to be challenging about logarithms is, in general, most calculators cannot evaluate logarithms for you. So you can evaluate something with an exponent, you can evaluate something with addition, subtraction, multiplication, division. You can even evaluate with different radicals, square root, cube root, fourth root, so on and so forth. Your calculator is limited as to how much it can do with logarithms. For the most part, it's only going to be able to handle anything that requires you using this particular logarithm and this particular logarithm. The other ones, you may or may not be able to type into your calculator. But the good news is most everything we're going to use logarithms for, these are going to be the only two we need in order to do what we need to be able to do. So we'll get there in a minute. We'll talk about how you plug things into your calculator, how you use that. So what is a logarithm? It's the inverse of an exponential, but what does it really mean in terms of an algebraic operation and what you're actually going to do when you see one? So the best way to understand what a logarithm is to think about how an exponential can be converted to a logarithm and vice versa. What does it look like to convert between one form and another? We understand what an exponential is because we understand how to apply an exponent. If we can think of every logarithm in terms of how it relates to something exponential, then it's going to be a little bit easier to understand what a logarithm is. So we're going to practice converting between something that has a logarithm and then the corresponding statement that has an exponential in it. So a couple things to remember, a couple little tricks to simplify the conversions. Number one, the base is going to be the same in both forms. forms. So if we have a logarithm, the base is going to be the subscript. So for instance, if you saw this is log base 10. So we're looking at a base of 10. So if I have a logarithm with a subscript of 10 and I want to convert to something involving an exponential, I'm going to have an exponential base 10. Now when we convert to something exponential, remember the base is the big number. If we look at an exponential expression, the base is the big number, the superscript is the exponent. So if we're converting from a logarithm to an exponential, we go from a subscript to the big number, and then vice versa if we want to go from an exponential to a logarithm. Now that's going to leave us with two other numbers in the problem. We're going to have an actual equation, an actual statement involving a logarithm or an exponential. The other two values in the problem, you can think of those as representing x and y. So for instance, if you see something like this, here's your base, b is your base. The other two numbers you can think of kind of like x and y. Well, if we're converting between an exponential and a logarithm, what we're doing is inverting. Remember, a logarithm and an exponential are inverses. We got to this logarithm by taking an exponential and inverting it. So the other two numbers in your statement, once you start to convert, the other two numbers are going to switch places across the equal sign. And that again is going to be based on the inverse relationship. Now, where they go once you switch them is going to depend on how you're converting, what you started with and what you're converting to. So we'll talk about that more when we look at an actual example. Now, what happens if you don't have an actual equation that's saying this log is equal to this? What if you just have a logarithm and you want to interpret what it means? You want to evaluate the logarithm, kind of like taking the square root of a number. You want to determine what it means, what it's looking for. I want you to think of a logarithm as asking a question. Anytime you see something algebraic to evaluate, it's asking a question. And the answer is going to be whatever value you would get once you answer that question. So the base, here's the question representing a logarithm. If we see log base b of x, this is the question it's asking. It's asking the base, which is b, to what power? There's the question part, to what power? The base to what power gives a value of x. So log base b of x is saying, if you take the base b, what power do you have to raise it to in order to get an output of x, or whatever number happens to be plugged into the logarithm? So if the question is, what is the exponent, what is the power, the answer to that is going to be whatever exponent makes that particular statement true. B to what power gives me x? Well, whatever exponent happens to make that true for the particular value of b and x that you have, that's going to be the value of the logarithm. That's going to be the output you get when you evaluate your logarithm. So we'll get there. Let's just start by converting though, and then we'll talk a little bit more about what happens when you're not converting and you want to just evaluate a logarithm as it stands just by itself. Okay, so let's start by changing from logarithmic form to exponential form. Okay, so here's our first statement. Log base 5 of 25 is equal to 2. So this is a true statement, but why is it a true statement? Why is that actually true? Well, we can decide why it's true. We can better understand this statement by converting it to something exponential. Okay, so I'm going to start with the actual logarithmic part. When I convert this, there won't be a log. It'll just be a base with an exponent. So the base of the logarithm, in this case, is 5. This is a log base 5. So when I convert this to something exponential, 5 is going to be the base of the exponential. Now the base of the exponential, remember, that's going to be the big number. So when I convert this logarithm to an equivalent exponential statement, the base of the exponential is going to be 5. Now once I take care of that, that leaves us two additional numbers in the problem. We have 25 on the left, we have 2 on the right. Think of these as representing x and y. It doesn't really matter which one is which, but think of them as representing x and y. When I go from a logarithm to an exponential, I'm inverting. I'm flipping my x and I'm flipping my y. So the x and y, whichever ones they are, those are going to switch places across the equal sign. Now let's focus on the 25 first. It's moving to the right. Now if we've moved the 2 over, there's nothing over here. So once the 25 moves to the right, it's just there by itself. It's just 25. Now when the 2 moves over, we have to think about what we got rid of and what we replaced it with. So we got rid of this logarithm base 5 and we replaced it with an exponential with a base of 5. So we now have a base of 5. But if it's supposed to be an exponential, what we're missing then, that we didn't get automatically, was the exponent. So when the 2 moves over to the left-hand side, the 2 is then going to be the exponent that goes with our base of 5. So log base 5 of 25 is equal to 2. Another way of saying that is 5 squared is equal to 25. Here's how we can verify that this is the correct conversion. This is the question this logarithm is asking. It's asking 5 to what power gives me 25? Well, in this case, 5 to the second power gives me 25. And the statement that I would write that then answers that question is going to be the conversion for the logarithm. So log base 5 of 25 is equal to 2. This is asking the question, 5 to what power is 25? Well, 5 to the second power is 25, and that's the statement we've written as an exponential. Okay, let's look at another one. Log base 2 of 1/4 is equal to -2. Again, this is a true statement. We just want to convert that statement to its corresponding exponential form. So we want to start with the base of the logarithm. In this case, the base of the logarithm is going to be base 2. So when we convert this to an exponential, the log base 2 goes away. We now have an exponential base 2. The other two numbers, in this case 1/4 and -2, are going to switch places across the equal sign. So the 1/4 moves to the right. There's nothing there at this point, so it's there isolated by itself. The -2 moves to the left. Now we already have our base of 2, and we want to form an exponential. So if we already have our base, then when we move the -2 to the left, that's going to be the exponent. So log base 2 of 1/4 is equal to -2. The corresponding exponential expression or statement would be 2 to the -2 power is equal to 1/4. Now once we convert it, we should have a statement that's true. The previous one you can probably look at and verify that it's true, but why is this statement true? Well, if anything, we can verify that the statement is true using the graphing calculator. If you were to take 2 to the -2 power, you want to verify that once that simplifies, it's going to simplify down to 1/4. So I'm going to take 2, I'm going to raise it to the -2 power. Remember, this is your negative button. This is subtract, this is negative. So raise it to the -2 power, and then we hit enter. Now it's going to give me a decimal. I can convert to a decimal, convert to a fraction. Go to the math menu, and then under the first sub-menu it says arrow frac, which means convert to a fraction. So I'm going to highlight that, hit enter, and this says take the answer from the previous line and convert it to a fraction. So I'm going to hit enter again, and sure enough, I get 1/4. The reason this statement works out the way it does, what does a negative exponent mean? A negative exponent actually means take the reciprocal of the base. So if my base is 2, that negative exponent tells me take 2 and flip it. So 2, its reciprocal is then 1/2. So 2 to the -2 says flip the 2, make it 1/2, and then apply an exponent of 2 to it. So if we were to take 1/2 and then square it, we would get 1/4. So that's why that particular equation is going to be true. Okay, let's go in the other direction. So what if we have an exponential and we want to write the corresponding logarithm? What's that going to look like? Well, same idea. Start with the base. So now we have an exponential. Identify the base. Here's the exponential part of this statement. 64 is equal to 4 cubed. Verify, of course, that this is true. The base of our exponential is going to be base 4. So that means when we convert to a logarithm, it's going to be a logarithm base 4 with a subscript of 4. Now the other two numbers, in this case the 64 and the 3, are going to switch places. So the 3 is on the side with the base. It's now going to move to the other side where we don't have the base. and then the 64 is going to move to the side with the base. Now I want you to be really, really careful when you write something like that. The 4 is a subscript. The 64 is on the same line with the log, so it's not an exponent attached to the 4. The 4 is a subscript, log is on the line, 4 is below the line, and then 64 is on the line again. So that's going to be our logarithm. That's going to be how we write that. So log base 4 of 64 is asking the question, our base, 4, to what power gives me 64? Well, 4 to the third power gives me 64. So the log base 4 of 64 is going to be 3. That's the exponent we would raise our base to in order to get an output of 64. Okay, one more. 1/8 is equal to 2 to the negative third power. This is true for the same reason that this was true. Remember, the negative exponent just tells me take my base, take its reciprocal, and then apply the exponent as normal. So 2 to the negative third is saying take 2, take its reciprocal, which would be 1/2, and then cube that. So 1/2 times 1/2 times 1/2 is going to give us 1/8. So that's why that particular statement is true. Now let's convert this to a logarithm. Here, our base is going to be a base 2. So the big number is 2. When we convert to a logarithm, that's going to be our subscript. So log base 2. Now remember, that's a subscript. So log is on the line, 2 is below the line. The other two numbers, the 1/8 and the negative 3, are going to swap. So negative 3 was on the same side of the base. It's now going to move over to the other side. And then 1/8 was not on the same side as the base, so it's going to move to the side with the base. It's going to become the input for our logarithm. So log is on the line, 2 is below the line, 1/8 is on the line again. So log base 2 of 1/8 is equal to negative 3. 2 to what power is equal to 1/8? 2 to the negative 3 power is equal to 1/8. So hopefully seeing the conversion makes it make it a little bit more sense. Again, a logarithm is typically a little bit mysterious the first time you see it because it doesn't represent an actual algebraic operation. We can take anything else we've seen so far and we can think of it in terms of an actual operation, something physically we can do as a procedure to whatever numbers we have in a problem, in an expression. Logarithms are a little bit different. You have to think of it in terms of an exponent, and again, think of the question that any logarithm is asking. So what happens if we get rid of the equal sign? There's unknowns. What happens when we want to actually determine what a logarithm means when there are unknowns involved? We're going to use the same kind of strategy. We're going to use this conversion strategy to help us understand what the logarithm means and what the different components of that logarithmic statement mean in relation to one another. So here's our first equation. Think of it as just solving an equation. That's really what we're doing. But in order to solve it, we have to understand what the logarithm means, which means we may have to convert it to something exponential. So our first equation, y is equal to log base 4 of 16. And we want to know what is y equal to without the use of a calculator, at least to evaluate the logarithm. Log base 4, your calculator doesn't have a log base 4. Your calculator has log base 10 and ln. What you cannot do is this. You cannot type log of 4 and then assume that that is log base 4. That's not what that means. This means take log base 10 and apply it to an input of 4. Not the same thing. So in order to understand what this means, we can think of converting the logarithm. Think of the question the logarithm is asking. The question it's asking is 4 to what power gives me 16? Or I can just think of doing the conversion. So taking this statement, which is logarithmic, and converting it to something exponential. So here our base is 4. If we convert it to an exponential, the big number is going to be 4. The other two numbers are going to switch places. So y is going to go on the same side of the base. We have a base, so that's then going to be our exponent. That's our unknown. And then 16 is going to swap places, move to the other side. So our corresponding question, we can again think of it in terms of a question, but now it's an exponential question. The question is 4 to the y, what would y have to be in order for 4 to the y to be 16? And the answer to that is going to be 2. So y equals 2 is going to be the value that makes this statement true. And again, we can think of it just in terms of the original, because the logarithm is asking us a particular question. It's asking 4 to what power gives me 16? Well, 4 to the second power gives me 16, so y is going to be 2. Now, what happens if we move our unknown to a different location within the logarithm? Same idea. Think about the kind of question the logarithm is asking, and or think about how you'd convert to something exponential. So log base 2 of x is equal to -3. So if we were to think of just the logarithm is asking 2 to what power gives me x? Well, in this case, we know the power is -3. It's equal to that. So if we were to take this statement and convert it to something exponential, that's going to help us understand what this is asking for. So my base in this case is going to be 2, so exponential base 2. My other two numbers are going to switch places, so -3 is going to become my exponent, and then x, once it moves, now I have my unknown isolated, which is a good position to be in. So we know that x, our unknown, is equal to 2 to the -3 power. And again, you can just evaluate this part in your calculator if you want, or think about what that negative exponent means. Remember, the negative means take the base, which is a 2 in this case, take its reciprocal, which would give us a 1/2, and then apply the regular positive exponent to that flipped base. So that would then be 1/2 cubed, which gives us 1/8. Now again, we can verify this in the calculator. So we have 2 raised to the -3 power. Hit enter. Okay, it's going to give me a decimal. So math, option 1, arrow frac, is going to convert it to a fraction, which is then going to be 1/8, which is what we get right here. So if we were to plug this back in place of x, we're saying 2 to what power gives me 1/8, if that's my value of x. Well, 2 to the -3 power gives me 1/8. So that verifies that this statement is now true based on this value of x. So the only other place we could put our unknown is going to be in the base of the logarithm itself. Now, we do have some specific requirements for what a logarithmic base can be, and they're based on our requirements for an exponential. So think about where the logarithm came from. It came from what happened when we took a basic exponential, something of the form y is equal to b to the x, and then inverted the x and the y. But notice the b still meant the same thing once we inverted. So the requirements based on b are still the same requirements even after we convert. So remember, when we talked about exponentials, we did have specific requirements for the base. 2 requirements. Number 1, the base has to be a positive number. We didn't look at any exponentials with a negative base because negative numbers don't necessarily behave all that well when we start raising them to different exponents. So the base has to be a positive number, something strictly greater than 0. We also decided that the base was not going to be 1. If we were to take a base of 1 and then just raise 1 to a bunch of different powers, nothing particularly exciting happens. 1 to any power is still just going to be 1, which means we don't really have something exponential. We don't have something that behaves and grows or shrinks in an exponential fashion. The most important thing here, though, is that b has to be a positive number. So if our exponential base has to be a positive number, then when we convert this statement to something logarithmic, and now that's the subscript, that subscript also has to be a positive number. B has to be greater than 0. That's going to be important for this particular one where we're solving for the base. So log base b, where b is our unknown, log base b of 100 is equal to 2. So if we think of this question, this is saying b to what power is equal to 100? Well, b to the second power is equal to 100. And again, if we convert it, the base of the logarithm becomes the base of the exponential. The other two numbers switch places. So 2 becomes my exponent, and then 100 is now what the expression is equal to. So we have b squared is equal to 100. Now, why did I make a point of mentioning the stipulations for the base? Why does that matter here? Well, technically, there are two different numbers we could square and give us 100. Remember, squaring just means multiply it by itself. So what would you multiply by itself to give you 100? Well, you could multiply 10 by itself to give you 100, but notice that you could also multiply -10 by itself and give you 100. You can verify this in the calculator. So if you were to take -10 and square it, now remember, if you're going to apply an exponent to a negative, put parentheses around the negative, so -10, and then we're squaring it. Notice that also gives you a 100. So which one is it? Is it both? Is it only one of them? Is it neither? Well, it's going to have to be the value of b that not only makes this true, but also meets the requirements we have for the base. Remember, the base has to be strictly greater than 0. What that means is that although b equals -10 solves the exponential equation, it does not solve the logarithmic equation because that base cannot be a negative number. So that means the value for b that we want is going to be b is equal to 10. So again, imagine plugging this back in. b is now 10. So the logarithm base 10 of 100 is asking the question, 10 to what power gives me 100? Well, 10 to the second power gives me 100. So our logarithmic statement is then true with a value of b is equal to 10. Okay, so we've talked about conversion, we've solved for some unknowns. Let's talk a little bit more about the other things that can happen with logarithms, and then we're going to finish by looking at some different types of equations other than these kind that we might see. We can use logarithms in a specific way in order to help us deal with maybe equations that have exponentials in them. Keep in mind, logarithms and exponentials are inverses. Inverses cancel each other out. An addition cancels a subtraction, a multiplication cancels a division, a logarithm cancels an exponential, and vice versa. So what happens if we have a little bit more going on with our logarithm? Say we have a logarithm and there's a bunch of stuff inside of it, or maybe we have multiple logarithms. We actually have some rules for logarithms that are going to allow us to simplify different expressions that involve logarithms. These are closely related to our exponent rules. So there are rules for exponents that are going to allow us to simplify in specific situations. So one of the rules for exponents tells us that if we were to take something with one base to a power, multiply by something with the same base to another power, then we can just add their exponents together. That's a standard exponent rule. We have rules similar to that, but they work for our logarithms. So we're going to use these. We can use these to simplify. We're going to focus on how we use these to solve equations. So two rules, two inverse rules. What do the actual inverse rules look like in the context of an actual situation in terms of an exponential and an associated logarithm being inverses? Well, here's how we use an inverse rule. If we have an exponential base b raised to the x power, and we apply the logarithmic function base b. Notice the b's are the same. That's important. They're going to have to be the same. If we apply the logarithm with the same base to it, then we get an output of x. What that means is that the logarithmic function base b reduces the base in the exponential function base b. And all it leaves us with is then going to be whatever was in the exponent, what we think of as the remainder, what's left over after those two components reduce. Now we could do that the other way around too. So this would be apply a logarithm to an exponential. What if we applied an exponential to a logarithm? That's what this would look like. This looks a little nuts. We have a logarithm inside of an exponential, which means it's now in the exponent. But it's the same idea. We have a logarithm base b, and then we're applying the exponential base b to that logarithm. It just so happens that when we apply an exponential, what we're applying it to goes into the exponent, because remember, the base is the fixed number, the exponent is where we plug things in. Well, as long as our two bases are the same, again, the exponential, the logarithm, they reduce. They cancel one another out. And so what we're left with in this case is also x. but in this case, x was whatever was inside of the logarithm. So biggest thing to remember, biggest takeaway there, we apply a logarithm of one base to an exponential of the same base, they cancel. We apply an exponential of one base to a logarithm of the same base, flip the order, they still cancel. Okay, we have a product rule, a quotient rule, and a power rule for logarithms as well. The power rule is going to be the most useful one for us, but the other ones are valuable in different situations as well. So the product rule tells us that if we have a logarithm with a product inside of it, we're going to think of m times n as being the input for this logarithm base b. If we have a product inside of our logarithm, then the product rule says we can actually split this up into two separate logarithms, each one applied to each of those things that were being multiplied, and we split it up into two logarithms that are then added. So the way I like to think of this is multiplication on the inside becomes addition on the outside. So log base b of m times n is going to be log base b of m plus log base b of n. Notice when we convert and split it up, the bases are the same, so it's still going to be base b no matter what. We're just splitting up that product inside the logarithm, and that's going to split it up into two logarithms that are being added. Well, not surprisingly, if multiplication splits up into addition, division, in this case a quotient, so a quotient inside of our logarithm, is going to split up into subtraction. So log base b of m divided by n is log base b of m minus log base b of n. One thing to keep in mind is multiplication and addition are commutative. What that means is you can do them in either order. So m times n times m, same thing, which also means that you could flip the order in which the logarithms were added. The order is not going to matter when we're talking about the product rule. The order absolutely matters when we're talking about the quotient rule. Notice the particular order these two logarithms are in. It's the logarithm of the numerator minus the logarithm of the denominator. Just like division, order matters. Something divided by something else is not the same if you flip it. Same thing with subtraction. One thing minus another, not the same thing if you flip the order. So the order is going to be very important if you use the quotient rule. The last one we're going to use is the power rule. This is going to be one that's going to be really important when we start to solve equations. So the power rule applies when we have an exponent inside of a logarithm. So log base b of m to the p power. M and p can be whatever we want. We're thinking of m to the p power as being the whole input for the logarithm. So it's all inside of the logarithm. Whenever we have an exponent inside a logarithm, the power rule tells us we can actually take that exponent and we can bring it out front, and it's then multiplied by the logarithm with just the number representing the input without the exponent. So think of it as just you can bring the exponent down. You can bring the exponent out front. It becomes a factor. It becomes something multiplied by that logarithm. The benefit of being able to use a rule like this is you may not be able to simplify this logarithm, but once you can pull p out, you may have something that's then easier to simplify, which will then get you closer to having a fully simplified final answer. Now, it's important to think of properties and rules as things that you can use in either direction depending upon the goal. So say, for instance, your goal was to take one complicated logarithm and break it down into smaller logarithms, little ones that you might be able to simplify on their own. Well, in that case, you would use something like the product rule or the quotient rule from left to right. That would take one big complicated logarithm and split it up into individual less complicated logarithms. That might be the goal. Maybe the goal is to split it up so you can simplify the individual components as much as possible. Your goal might also be to combine things together into one logarithm. That's typically the goal when you want to solve an equation. You want to combine things together, which is then going to make things easier to isolate if they're combined together into one expression. If the goal is to combine the logarithms together, then you're going to use these rules right to left. So if you saw two logarithms that are added, as long as they have the same base, you can combine them together into one with multiplication on the inside of that logarithm. If you see two logarithms that are subtracted with the same base, you can combine them together with one with division on the inside. We can use any combination of these rules. We can use them in either order, just depending on what our goal is, what we actually want to accomplish. So let's look at a few different equations. Equations like this can get complicated depending on what situation you're in. We're going to focus on just basic equations and getting a sense of the structure for what these problems look like, how a logarithm and how an exponential interact. So if we have a logarithmic equation, the equation has a logarithm in it, probably the easiest way to solve is going to be to convert the logarithm into exponential form. In a lot of cases, we can solve equations just plugging things into the calculator. Well, the problem with that for logarithms is we're limited as to how much we can plug into the calculator when it comes to a logarithm. All we have is log, which is log base 10, and ln, which is natural log, log base e. So we're limited there. But by taking something logarithmic and converting it to something exponential, our calculator can handle exponents all day long, and typically we end up with something we can simplify then. So anytime we have an equation with a logarithm in it, a good place to start is just start by converting it to something exponential. Now, if we have something exponential, what we're going to use is this fact that exponentials and logarithms are inverses. An exponential of a particular base is reduced or canceled out by a logarithm of a particular base. So whenever the bases match, this is what the inverse rule says, whenever the bases match, they essentially just cancel each other out. Log base b, exponential base b, they just cancel out. So if we can use that kind of rule, we will. Now, there will be other situations where we can't directly use a rule like that. That kind of rule can only be used in conjunction with the calculator if we're going to use log base 10 or log base e, because again, those are the only things we have buttons for. The good news, though, is that we can kind of finagle a little bit. We can use some of those log rules other than the inverse rule in order to take something that maybe doesn't immediately fit in a calculator and put it in a form that we can actually use in the calculator. So regardless, when it gets down to it, if you have an exponential, you're either going to apply log, which is log base 10, or ln, which is going to be log base e to it. Even if the base for the exponential is not a 10 or an e, you're still going to apply one of these. We'll talk about why in just a second, but ultimately it comes down to being able to do something in the calculator. Those are the only two logarithms we have represented in the calculator, so we're going to use those two so that the calculator can then be applied so we can finally get an answer for our problem. So let's look at several different situations, several different examples, different forms, different numbers. We want to solve for x to 4 decimal places, which means we're then, of course, going to have an answer in the calculator. We'll round to 4 decimal places. Okay, so our first equation, log of x is equal to negative 2.315. Okay, so what is our base? It's not written. That's not a mistake. It wasn't left out. Remember, when it's not written, it's understood to be a base 10. We just don't write the 10 because the standard abbreviation, because we use base 10 so much, is just write log without the base. So anytime we have a logarithmic equation, we want to solve for x in this case, which is the input for the logarithm, we're going to start by converting to the corresponding exponential form. So the base of the logarithm, in this case, is base 10. Remember, it's implied, it's not written. So when we convert to an exponential, the big number is going to be 10. That's going to be the base of our exponential. The other two parts in the equation are going to switch sides. So x switches to where it's isolated, and then negative 2.315 becomes part of the exponential. Well, we already have the base, so that's then going to be the exponent. Notice the benefit of converting here, though. We went from having the x in the middle of the equation, where ideally we want to isolate it, we want to get it by itself. By converting, automatically the result is that the exponent, or not the exponent, the variable is now isolated. So it accomplishes what we want in that sense. And then it also gives us something that we can plug into the calculator. A base, an exponent, you can plug in any numbers you want that are structured like that. So let's see what this is going to be. So we're taking 10 and we're raising it to the negative 2.315 power. Okay, so to 4 decimal places, that's going to be 0.0048. That's going to be roughly what makes this particular expression true. Now, it's always a good idea to plug things back into the equation to double check your answers. What would that look like in this case? Well, we're plugging this is what we're saying x is equal to. We would have to plug that into log base 10. So here's how we could do that. If you hit log, that's going to open up log base 10. We want to take log base 10 of what we're proposing is our answer. So I'm going to take this particular number, I want to plug it into the logarithm. Rather than having to retype it though, I can use second and negative, which is going to put the answer from the previous line into my current line. So I'm taking the logarithm of my previous answer, I hit enter, and then notice what it gives me, negative 2.315. So that verifies that this x is in fact what solves our equation. Now keep in mind, if you just checked with the rounded version, what would happen? So log, and then say you plugged in the rounded version, which is 0.0048. What's going to happen? Notice it's going to be a little bit off. So we go from negative 2.315, which is exact, to negative 2.319. So it's really close. You might see this and think maybe it's wrong though. Well, it's not. It's wrong. Technically it's wrong because we rounded at the very end. The rounding directions were followed, so that's okay. But when we take a rounded answer and plug it back in, we're going to get a result that's slightly off from the original numbers in the equation. So just keep that in mind. If you check with exact numbers, you'll get exact answers. If you check with rounded answers, you're going to get another rounded answer. Okay, let's look at another one. Natural log of x, ln of x, is equal to 2.386. Structurally, these two equations are the same. What's changed is the type of logarithm we have. So remember, this is going to be log base 10. ln means we're looking at a log with a base of e. So I want to convert this equation to something exponential. My base is e, so my exponential base is also going to be e. The other two numbers are going to switch places. So 2.386 is part of my exponential. It now becomes the exponent. And then x is automatically isolated by that conversion. So x is equal to whatever this number is. So let's plug that in. Now remember, there's two different places to get e. You can get an e by itself right above the division symbol, or you can get e with an exponent right above ln. There's a reason log has a 10 above it and ln has an e above it. That's because those are the bases that go with those two logarithms. Now this e is going to give me the exponent automatically, and I know I'm going to need an exponent, so I'm going to use that one. So second and ln types the e and gives me the exponent automatically. I want 2.386. So 2.386, and enter. And to 4 decimal places, that's going to be 10.8699. Now again, if we want to check this answer, plug it back into the original equation. So we're taking the natural log of this number. So I'm going to copy it. Second, negative copies the answer from the previous line. And when I simplify that, that's going to give me 2.386. So that verifies. So anytime we have something logarithmic, that's how we're going to handle it. Now in these particular problems, it doesn't matter if it's log or ln or any logarithm. It could be a log of any base. It doesn't have to be logarithms represented in the calculator, because notice when we converted to something that's not really dependent on having that particular logarithm in the calculator. Say we had a log base 4. Well, that converts to an exponential base 4. That just means you're going to type a 4 and then the exponent that goes with it. So having a logarithmic equation with a particular base is not going to restrict your options in terms of using your calculator. You may not be able to check your answer by plugging it back in if it has a base other than 10 or e, but you can still do the problem, you can still solve for x. Now, what if we have an exponential equation? Let's look at a few different situations. So here we are very dependent upon what our calculator can do. We're using inverses again. So the inverse of a logarithm is an exponential. The inverse of an exponential is a logarithm. So we're going from exponentials to logarithms, which then means if we want to use the calculator, we're limited because now we have a logarithm and we know we only have 2 logarithm buttons. Now 10 to the x is equal to 2. In other words, we want to know what exponent would this have to be to make this statement true. I want to use a logarithm to simplify this particular equation. Essentially, I'm going to use this property of equality. You do one thing to one side, you do the same thing to the other side, you keep the equation in balance. I want to use that in conjunction with this idea of the inverse rules. The log base b applied to an exponential of the same base, well, the logarithm and the exponential cancel out, and all you're left with the is with the exponent. Why does that help here? Well, notice where our variable is. It's in the exponent. So if we can get rid of this base of 10 and keep the exponent, then we'll be right where we want to be. A logarithm is going to allow me to do that as long as the logarithm has the same base. So if this is base 10, then I want to use a logarithm base 10. So I'm going to apply the logarithmic function base 10 to both sides of the equation. It's going to be important that you do it to both sides, otherwise you unbalance the equation, you're not going to get the right answer. Why did we not have to do something like that here? Well, here we weren't applying an operation to both sides, we were rearranging the equation and writing in a different form. Here, we're truly using an inverse operation. We're applying a particular operation to one side, so we have to apply it to the other side of the equation to keep things in balance. So base 10, I'm going to apply logarithm base 10, and then I do it to the right-hand side as well. Now, why do I do that? What does that accomplish? Well, now I have a log base 10 applied to an exponential base 10. That inverse rule says those two operations cancel one another out. In this case, just leaving us with the exponent, which is x. That was our goal. Now, what about the other side? The other side is now what x is equal to. So the left-hand side simplifies down to just an x. The right-hand side of the equation is what x is equal to. It's equal to log base 10 of 2. Now, log base 10 of 2, say it asked for your exact answer. Say you were typing in your answer and it said give exact answers. This is the exact answer. If you go any further than that, it's just going to be an approximation, which is fine here. But if it asks for an exact answer, you stop right there. You don't need anything else. Log base 10 of 2 is the exact answer. Kind of like if you got an answer of the square root of 2, something like that. Anything else you do with the square root of 2 then just requires approximation. So if you wanted something exact, you just leave it as the square root of 2. Same kind of thing here. But we do want an approximation, so we're going to take that and we're going to plug it into the calculator. So log base 10 of 2 is going to give us 0.3010. So we're saying 10 raised to this power supposedly gives me 2. Let's verify that. So 10 raised to this power, copy and paste. So second and negative copies that answer. 10 to this power should give us 2. And sure enough, it does. Now, what about 10 to the rounded version of our answer as opposed to the exact, the rounded version? So 10 raised to the 0.3010. We get something really, really close to 2 right underneath it. Why is it less than that? Well, the number we gave as an answer, notice that it's smaller than the actual number we have in the calculator. So that means the output we get when we plug it back in is also just a little bit smaller. But it is close to the actual answer we'd expect, so that's verification. Okay, let's look at another one. e to the x is equal to 3. Again, same kind of structure. But here, if we want to get rid of this base of e and keep our exponent, our x, now it makes more sense to use natural log. We used log base 10 here because the exponential had a base of 10. Here our exponential has a base of e, so it makes more sense to use log base e, otherwise known as ln. I have to do the same thing to both sides of the equation to keep it in balance. Now on the left-hand side, log base e applied to exponential base e. Those two operations reduce, leaving us with just our x. And then x is equal to the natural log of 3. Now again, if you wanted exact answers, that is your exact answer. You leave it alone. If you want the approximation, plug that into your calculator, but this time we're using ln. So ln of 3 is going to give us 1.0986. And again, let's check it. So e to that power, sure enough, gives us 3. So that verifies that our answer is correct. Okay, one more. This one's a little bit different. We'll use the same kind of strategy, but we're kind of limited as to what happens from there. So we had 10 to the x, we used log base 10. We had e to the x, we used log base e, otherwise known as natural log. Here we have 3 to the x is equal to 4. So we want to know what exponent would we need to raise 3 to in order to get an output of 4. Well, let's think about what would make sense here. If we raise 3 to the first power, we're going to get an output of 3. What happens if we take 3 and square it? Well, then we're going to get an output of 9. We want an output of 4, which is somewhere between those. So an exponent of 1 is too low, an exponent of 2 is too high. So more than likely the answer we get is going to be somewhere between 1 and 2. Let's see if that is in fact verified once we go through the algebra. Now, if I wanted to just directly cancel out the 3, I would need a log base 3. Log base 3 applied to exponential base 3, they would cancel out. What's the problem with using a log base 3 though? Well, we want to round. Remember, we want to solve for x to 4 decimal places. If I use log base 3, think about what's going to happen on the right-hand side. I'm going to have something that looks like that. These were two things that I then typed into the calculator. But if I have a log base 3 on the right side, I don't have a way to type that into the calculator. So it would make the problem a little bit easier. It'll isolate x, but it then gives us something that we can't type into the calculator. So here's a way around that. As it turns out, we don't actually have to have the exact logarithm with that exact base to do what we need to be able to do. What we're going to use now, instead of using the inverse rules, we're actually going to use the power rule. Remember, the power rule says if we have a logarithm applied to something with an exponent, then we can actually take that exponent and we can pull it out front of the logarithm and make it a factor. So if we apply that here, then if we apply a logarithm to 3 to the x power, that rule tells me, regardless of what the base is, if I apply a logarithm, I then have something structured in such a way that I can pull my exponent out. Why is that beneficial here? Well, exponent, the exponent is the x, it's what we're trying to solve for. So by applying a logarithm here and using that power rule, we're going to be able to isolate the x the way we need to. Ultimately, it does not matter which logarithm we use. That particular rule, the power rule, is not dependent upon the base of your logarithm. What you do want to choose, though, is one of the two logarithms that you're going to be able to plug into the calculator, either log base 10 or natural log, log base e. The one you choose doesn't matter, and I'll show you why in just a minute. Let's just use log. That's what I used here. So use log base 10, again, because that's in the calculator. I have to do the same thing on the left and right hand side of the equation to keep it in balance. Why does that help? Well, here's what does not happen. Log and 3 do not cancel. This is log base 10. This is an exponential base 3. That would be like taking a cube root and something to the 10th power. Nothing cancels. It doesn't work that way. So that's not what happens here. But what does happen is the simplification resulting from the power rule. The power rule says we have a logarithm that has an exponent inside of it. We can pull the exponent out front, and that's what we can do here. So this exponent of x can then be pulled out front, which then just leaves us with log base 10 of 3. Again, that helps because now the x is in a position where we can solve for it. Log of 3 is just a number. So all we really have on the left-hand side is x multiplied by a number. It's not a pretty number, but it's a number. It would be like something like the square root of 3. It's not pretty, but if you see it, you can do exactly what you do to just a regular 3. You can do that to the square root of 3 or to log base 10 of 3. So if it's a number multiplied by x and the goal is to solve for x, well, we need to divide it out from both sides. So that's going to give us x isolated is equal to log of 4 divided by log of 3. Now, another thing that you cannot do there that's very tempting, that's not allowed, you cannot cancel log and log. Log is not a number. Log represents an operation. That would be like taking the square root of 4 and the square root of 3 and saying that the radical symbols cancel. They don't. Log means we're doing something. Log represents an operation. So operations do not cancel. Numbers that have common factors cancel. Nothing cancels here. This is the exact form of the answer of the value for x, and it's as simple as it's going to go without approximating. So log base 10 of 4 divided by log base 10 of 3. That's going to be our exact answer. So let's plug that into the calculator. So we have log of 4, and then make sure you close your parentheses once you finish that, because then we can directly divide by log of 3. And there we go. So 1.2619, that 5 tells us to round the 8 up to a 9. Now we're saying that 3 to this power should give us an output of 4. Notice this is between 1 and 2. Remember, 1 as an exponent would be too low, but 2 as an exponent would be too high. It's somewhere between. Let's verify that it does in fact work. So we're taking 3, we're raising it to this power, and sure enough, it gives us an output of 4. So that verifies that that particular value of x does solve the equation. Now I used log here. Why did I use log? Well, I used log because I had a button on the calculator for it. We also have a button on the calculator for natural log. So what if I had used natural log here instead? What would change? What would stay the same? Well, if I'd used natural log over here, natural log over here, okay, so those logs now become ln's. The fact that it's an ln rather than log base 10, does not change how I can use the power rule. It's still a logarithm. It still has an exponent inside of it. I can still pull that exponent down based on that power rule. The only difference after using the power rule is now I have x times ln of 3 is equal to ln of 4. So the only difference is all the logs would become ln's, and then same thing for the final answer. It would just be ln of 4 divided by ln of 3. Well, in theory, if we're saying that this particular solution technique works the same way, we should get the same answer. Let's see if we actually do. So let me type in log base 4 divided by log base 3. That was how we did it before. That was the answer we got. What if we used ln? Well, now it's just going to be ln of 4 divided by ln of 3. And look, we get the exact same answer. It's not dependent upon the type of logarithm we use to actually use this particular technique. As it turns out, we would get the same answer regardless of the base we used. The fact that the logarithm has the same base in the numerator and denominator is why we end up with the same answer at the very end. So if the calculator could handle other types of logarithms, you could use any type you want and you're going to get the same final answer. So this wraps up our general discussion of functions. So we looked at polynomial functions. We take 2 and we write them in a ratio. That gives us a rational function. We talked about exponential functions, different than polynomials. Remember, polynomial means we're plugging in our variable to the base. The exponents are fixed numbers. In an exponential, the base is the fixed number, and when we plug in inputs, they go into the exponent. Very different graphs. And then here we've talked about logarithms. A logarithm is just the inverse of an associated exponential. A logarithm cancels an exponential cancels a logarithm whenever the bases are the same. We can convert to one form or another, and that's going to help us better understand this idea of a logarithm.